So, have you ever really stopped to think about how your computer actually gets anything done? Is it like a super meticulous chef, carefully following a recipe step by step? Or is it more like a master juggler, keeping a dozen things in the air at once? Well, that's the core of what we're talking about today. Serial versus parallel execution, and believe me, it's a nonstop race against time.
Okay, so stick with me here. What on earth does cooking a meal have to do with running a computer program? I know, it sounds kind of random, right? But the answer is pretty much everything. And getting that connection is the secret sauce to making our computers unbelievably fast.
So let's start with the basics, the way that just makes sense to us humans, doing things one step at a time.
All right, so imagine any program you use is just a fancy recipe. You've got your ingredients, that's your data, you've got the instructions, that's the source code, and then you have the chef, right? The CPU, the processor, who's actually doing the work, following every single instruction to cook up the final dish, your program's output. And just like in the kitchen, the order you do things in is absolutely crucial. I mean, you can't frost a cake before you bake it, right? It matters a lot.
And that one thing after another approach, that has a name. It's called serial execution. It's super simple. The next task literally cannot start until the one before it is 100% done. It's kind of like doing laundry when you only have one washing machine. You have to wait for that load of whites to finish its whole cycle before you can even think about throwing the dark scent.
Now, the great thing about this method is how simple it is, right? It's totally predictable, easy to follow. But, and this is a big but, there's a huge catch. It just doesn't scale. Your performance is completely bottlenecked by how fast that one processor can go. You've basically hit a speed wall. You just can't get any faster.
So, if doing things one by one is too slow, how do we smash through that wall? Well, that brings us to this really powerful idea: doing things in parallel.
And this, right here, is the game changer. Let's go back to our laundry problem. Instead of being stuck at home with your one machine, imagine you go to a laundromat. Bam! Now you've got, say, 4 washing machines. You can run all 4 of your loads at the exact same time. The whole job gets done in the time it used to take to just one load. That, my friends, is the magic of parallelism.
Okay, but hold on. You can't just throw parallelism at any old problem. There are a couple of rules. First, the tasks have to be independent of each other. Think about it. Washing your towels has nothing to do with washing your sheets, so you can do them at the same time, no problem. And second, you've got to have the right hardware for the job. You need those multiple washing machines, or inside a computer, you need a multi-core processor.
All right, let's put this into practice. And what better way to show the incredible power of going parallel than with a high-stakes action movie, save-the-world kind of scenario.
Here's the setup. The mission: an FBI agent has to crack an 8-digit password. Simple, right? Except the fate of the entire world is hanging in the balance. The clock is ticking. So they fire up a single powerful computer to try every single combination, one after another, the serial approach. It chews through the possibilities and finds the password in 64.6 seconds. Now, in the real world, that's pretty darn fast. But in this world,
It's just not going to cut it. As Agent 008 shouts, "I only have a couple of minutes before the building will burst into flames. Speed it up." So yeah, the problem is painfully clear. Serial execution is just too slow to save the day.
So what's the solution? You guessed it, go parallel. I mean, think about it. Checking the password 12345678 is a completely separate job from checking 8765431. The tasks are totally independent. So what do? They chop up all the possible passwords into chunks, and they give each chunk to a different processor core. Now they're all checking at the exact same time.
But wait, here's where the story takes a really interesting turn. You might think, great, just throw more processors at it. But you can't just add an infinite number of them and expect infinite speed. There's a catch. There's a speed limit to parallelism.
I mean, it seems logical, doesn't it? If 4 processors make things way faster, then shouldn't 4,000 processors make it 1,000 times faster? It makes sense. But the surprising and kind of weird answer is nope, it doesn't work that way.
And the reason why has to do with something called Amdahl's law. It sounds complicated, but the idea is actually simple. Imagine you and a bunch of friends are trying to find one specific index card in a giant pile. The actual searching part, that's parallel. Everyone can grab a stack and look through it at the same time. But what about the parts that can't be done in parallel?
Like one person has to divide up the pile at the beginning and one person has to collect the results at the end. Those parts become a huge bottleneck.
And that's the bottleneck right there in action. When you look at the numbers, you see that as you add more and more processors, sure, things get faster, but the jump in speed gets smaller and smaller each time. It's the classic law of diminishing returns, because you're always held back by the parts of the job that just have to be done one at a time in sequence.
So, here's the big takeaway, the thing to remember. A parallel program can only ever be as fast as its slowest non-parallel part. It's that old saying, right? A chain is only as strong as its weakest link. Well, here, a program is only as fast as its slowest link. Okay, so now that we get the speed limit on doing things all at once, let's clear up one final really important point. This is something that trips a lot of people up. You hear the words concurrent and parallel thrown around like they're the same thing, but in the world of computing, they are absolutely not.
Concurrency is all about how you structure your work. It's about dealing with many things at once. Let's go back to the kitchen. Imagine one cook. They chop a bit of salad, then they run over and stir the soup, then they go back to chopping the salad. See? They're juggling tasks. They're making progress on multiple things over a period of time. But at any single frozen instant, there's still just one person doing only one thing.
Parallelism, though, is different. It's not about structure, it's about execution. It's about actually doing many things at once. So now picture two cooks in that kitchen. One is over here chopping the salad, and at the exact same moment, the other is over there stirring the soup. That's parallelism. It's happening at the same time, and it absolutely requires more than one resource to pull it off. You know, there's this fantastic quote from the computing legend Rob Pike that just nails it. He said, "Concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once." It's so simple. Concurrency is the plan for how you're going to juggle everything. Parallelism is actually having enough hands to do it all at the same time. And that really brings us to a final kind of philosophical question. We've seen that one approach is all about managing complexity, and the other is about pure raw speed. So, as our world just keeps getting more and more complex, what do you think is going to be more important? Our ability to deal with more and more things at once, or our ability to actually do those things faster? It's definitely something to chew on the next time you're staring at a loading bar, wishing your computer would just hurry up. Thanks for diving into this with me.